Hi everyone and welcome to this video. Today we are going to discuss logistic regression, and we are just going on with our series on machine learning techniques. So far we've been able to introduce the concept of machine learning. We've been able to cover linear regression in detail and had examples with Python and also R. We also introduced some definition of terms that we commonly use in machine learning, and so how do we evaluate models using classification that are built for classification. So today we are talking about logistic regression, and this is an extension of the linear regression, albeit now our response variable is binary, where we are having responses 1 and 0. So in this set of video, we'll talk about the introduction. Then in the subsequent video, just implement an example with Python and R, just as we did using in linear regression. So just as a quick introduction, linear regression is a statistical modeling technique, and we use to predict probability of a binary outcome. Unlike in linear regression, where we were predicting now a continuous element, here we are having probability of being in a class binary 0 or 1. So it's an extension of the binomial distribution, where we are having either 1 or 0, a binary outcome. So why am I saying it's a modified version of the linear regression? We'll be able to see it later, because here now our dependent variable is categorical rather than continuous. Logistic regression has several outcomes, has several applications rather, and across various fields. One of them is healthcare, and in healthcare we are having, for example, prediction of a disease, whether somebody has a disease, cancer, yes or no, whether person has passed on, yes or no. Then we're also in finance, where we are having fraud detection, whether a transaction is fraud, yes or no, or as an individual defaulted a loan, yes or no. We also have it in classification of in finance, where individuals are being able to assess whether they are creditworthy, yes or no. We can do it in e-commerce and also employee attrition rates, where we are saying we are looking whether employees will leave a company, yes or no. So onto the equation now. So remember, in our linear regression equation, we had the distribution here. We had y equals to beta naught plus beta 1 x1 plus beta 2 x2 for our continuous, and then we also had an error term. So what I'm talking about here, beta naught, was what we call the y-intercept, where we were saying it's the expected value when everything else is when all the x's are 0. Then we talked about now beta 1 being beta 2 and so forth, until beta k being the coefficients of the x. So when we come to logistic regression now, we are now entering into a concept we call the generalized linear models. And in the GLMs family, it's where we say that for each model is just can be extended using the exponential family. So we can take this output here and put it under an exponential function, and it will be able to convert it to given a certain criteria, whether the binary output is binary, whether it's multi-class and so forth, whether you are modeling counts and so forth. So what we have the section where we have the continuous variable, so beta 1 x1, beta 2 x2, beta naught. That's part of the equation, is where we call the fixed component. We have the fixed component, so we assume that this side assumes it's from the normal, it follows the normal distribution, and here is the fixed outcome. However, the variability is brought by the error terms, the e that we add. So that e is what we call the stochastic component. So for a logistic regression, and this is something we'll be covering later on, the family generalized linear models, we have a function which we call the sigmoid function, that is used to convert this section into now this, where we are having now log p over 1 minus p, which we are calling the odds, the log odds that will be now interpreting in our equation. So what happens once we have our equation in the linear component? We now use this function, which is 1 over 1 plus e raised to negative. Now the component of the equation, what we'll call now this our link function, will be able to convert now this one into what? Into now the logistic component that we want. So a detailed discussion of this will come later when we'll be discussing the GLMs. So this is what happens with the sigmoid curve. Remember, just converts the linear component into now the probability odds for our observation. So what happens? Let's say you have this example, which is the linear model. If you are drawing it, we'll draw it straight like this. However, remember our conditions are 0 and 1. So here now we are discussing now how the sigmoid function works. So it takes the value and then outputs a value between 0 and 1. Then what happens now? We are mapping the value z to be between 0 and 1, and it's centered at 0. Then it's differentiable, and it's useful for optimization. We'll see this later when we're talking about the GLMs. But now we can use it for various functions. So we can see we have probit, we have logistic, we have complementary log response function, and this is what we'll be talking about later in the GLMs. So just as in summary, so what it happens, rather than when we have a distribution of x and y here, y versus x, if you are drawing a linear curve, it will be just a straight line like this. But this won't give a clearer picture, because remember we have only 0 and 1. What happens about 0.2, 0.4, 0.6? So what will happen with when we put it now into the sigmoid function, it will convert the linear model into a logistic model, which we have the orange curve here. Then we set that probabilities that are 0.5 and above are rounded up to 1. Those below 0.5 are now set to 0. That's what happens. So why don't we use linear regression for classification tasks? So one of the assumptions that we talked about when discussing linear regression was that we have non-normal error terms, where we are saying the error terms, E comes from follow a normal distribution, and we expect them to have a fixed mean of 0 and variance 1. So that's what we expected. So it's from a standard normal distribution. So if we have our equation, which was y minus, if we have now unsubstitute and solve for E, take E to the other side of the equation, we'll have yi minus the into bracket beta naught plus beta 1 xi. So when we have y equals to 1, what will happen? So when we replace y by 1, we'll be having the value of ei as 1 minus beta naught minus beta 1 x1. And when yi equals to 0, we'll be having the negative. So what does this show? So here, what we are calling the error terms, which is the difference now of the residuals, are not, it's varying. So we have two possibilities of the error term, which is not something that we wanted. We wanted them to be constant, and we have constant of variance, and they should follow a normal distribution. So this is what we have. So remember, we had for our error terms, we needed the residuals to be normally distributed. So but when you come to a logistic, it's a little bit difficult to follow the normality that is required. So the same holds to the constants of variance. Remember, how do you compute variance? It's the expectation of yi minus expectation of yi squared. So this is what we have as the computation of variance. So if we replace the formula into the equation of the linear regression that we are trying to implement here, we'll see that our variance won't be constant, and it will show that we'll be having two values for the variance rather than, and this violates the assumption of the linear regression. Another problem why we don't now use linear regression for binary options is that since the response function represents probability, so we are talking about constraints on response function. So since the response function represents probabilities, when the outcome variable is a 0 or 1 in indicator variable, the mean responses of probability should be constrained as follows. So what does it mean? We have 0 and 1. So our limit is between 0 and 1. So we expect that the value of the mean of y should be between 0 and 1. On the other hand, the mean response for the linear regression, how do we find it? We find it as the expected value of this, which is beta naught plus beta 1 x1. I think I just forgot a bar here, but this is the value of this. And this, the value in a linear regression, the mean of y, the mean of the expected response, cannot lie between 0 and 1. So what will happen? So for a regression line, this is what will be happening. But now for probabilities, we want it to be either 0 or 1. So for linear regression, it will go below 0, and this is a problem, and this is a problem, and therefore, thus for classification outcomes for binary responses, we cannot use linear regression. So in summary, the reasons why we cannot use linear regression is due to the non-normal error terms. Also, the second one is due to non-constant error variance, and the last one is the constraint on the response function. So quickly, assumptions of the logistic regression. So we are talking about the binary outcome, the binary response. Then of course the linearity of the log odds. So when the log odds are linearly related to the independent variables. So we are using a sigmoid function. However, the output, when you come to this component here, it's all coming from a linearized function. So what we are calling now the GLM, and this is what we'll be discussing later, but it's an assumption that must hold. So we also have independence, of course, independence of observations. Then we also strive to avoid multicollinearity, and this just adds noise to the model. Then there's always about large sample size, and this is just an assumption that's not easily held sometimes, but it's good to have just a large sample size. And then we haven't defined how large is large, but this is just an assumption we can hold for now. How do we fit a simple logistic model? So a simple logistic model, we've just mentioned that now what we are taking now, considering the sigmoid properties from a Bernoulli distribution, we can fit a logistic function. So we have the Bernoulli distribution equation. So from that we can be able to fit using the sigmoid function. So how does the Bernoulli distribution look like? So we have the probability of x being equal to what? So we have the probability of x ranging between 0 and 1, and then we can be able to convert it now. It has two values between 0 and 1, so it's the probability of p raised to k, then 1 minus p raised to 1 minus k. So that is like p raised to x, then 1 minus p raised to 1 minus x. So that's what we have. So the distribution of the error term depends on the Bernoulli distribution and the response. Thus, it's preferable to state the simple logistic model in the following fashion. So yi are independent Bernoulli randoms with expected value of pi, where now we have pi being here, expected exponential of beta naught plus beta 1 x1, then over 1 plus the exponential, now the numerator that we had there. So I know this may be too much, but will be easy when we are going to fit the model. It will be a little bit easier. How do we interpret now the function? So this is how we are fitting the model, but how do we interpret it? So okay, this didn't need, but when I upload the codes, you'll be able to see it. So the reason that the effect of the unit. So how do we interpret this? So the estimated regression coefficient beta 1 in a fitted logistic response is not straightforward as a slope interpretation, where we are saying given a unit increase in let's say x1, we expect y to increase by this. So it's not as simple as that. So in logistic regression, according to the location of the starting scale, so we consider the value of the logit response function at beta naught plus beta 1 xj. So we consider that's as our start. So what will happen? So the equation that we have, we now take something we call an odds ratio, which will be the difference between the odds at the second position and the odds at the first position. Therefore, so that we'll be having, which will be now odds 2 over odds 1, which is the exponential of the estimate coefficient that we'll be having. So how we'll be interpreting this is that given a unit increase in, let's say, x1, the odds of an event occurring, the odds of maybe the odds of the disease occurring increases by, let's say, 0.2. So that's what we'll be having, the odds increasing and the odds decreasing. So we have some references here for extra reading, and in the next set of videos we'll be now implementing an example in R and later also in Python, so that you can be able to see how we implement this concept of logistic regression. There you have it. Thanks for watching this video, and I hope to see you in the next one.